Now, let's discuss the functional description of the VSAT hardware and the hub station. A very small aperture terminal, also called integrated terminal or microterminal, consists of three main subsystems, namely the antenna, the outdoor unit, and the indoor unit. The outdoor unit is connected to the indoor unit by an interfacility link, IFL, in the 1 GHz frequency range. The IFL coaxial cable carries the transmit signals, the receive signals, the status and control signals, as well as the power. The antenna subsystem consists of the reflector, the antenna mount, and support structures. Various mount options are available depending on applications. They include pole, wall, and non-penetrating roof mount options. The outdoor unit, ODU, is a compact weatherproof integrated package mounted directly at the antenna focal point so as to reduce transmission losses between the antenna feed horn and the RF equipment. It contains all the RF and IF electronics, including the feed, the SSPA, LNC, and the IF amplifiers. This unit also has frequency agility, which allows access to the full satellite band of 500 MHz. The indoor unit, IDU, contains the baseband processor and the user interfaces. The processor performs the multiplexing, encoding, and modulation functions on the transmitted signal. In the receive mode, the demodulation, decoding, and demultiplexing functions are performed. The multi-port design of the IDU allows easy expansion to match growing or diverse traffic needs. The multi-protocol design enables flexible operation within various telecommunications environments. A typical terminal is configured with a 1.2 to 2.4 meter antenna depending on applications and geographical locations. The ODU would include a 1 to 3 watts high power converter and an 80 to 250 degrees LNB or LNC. For KU band applications, the IDU is typically designed to support a 56 kilobits per second data stream with 1/2 forward error correction. Now, the VSAT hub station. Functionally, the hub in a VSAT network must support network communications with remotes, hub remotes, and between remotes, remote to remote via hub, by routing, monitoring, and controlling the information transactions for all network users. Network operations is a management function provided by the hub. This function involves long and short-term issues. Long-term issues include network growth or resizing, network traffic loading and connectivity, network reconfiguration, operation, and maintenance strategies. Short-term operational issues include traffic and availability statistics, operation, and maintenance actions. The cost tracking function within the network is another management function provided by the hub. This function involves the collection, processing, and logging of cost and billing data. Finally, the hub supports the network monitoring and control functions by continuously keeping an eye on the remote VSATs and its own equipment in order to ensure a smooth operation of the network. Like the remote micro-terminal, the hub station consists of 3 major subsystems. These include the antenna, the IF and RF, and the baseband subsystems. Unlike the micro-terminals, the hub has some intelligence which resides in the network control center. The Network Control Center essentially consists of a network control processor, which is a mini computer loaded with the network communications, network management, network monitoring, and control software. This software allows the hub to support the functional capabilities described previously. The antenna assembly may consist of a reflector, typically 3.7 meters to 11 meters, depending on applications, the antenna mount and support structures, a 2 ports or 4 ports feed, depending on frequency reuse requirements at the hub, the motor drives for elevation and azimuth alignments, the antenna foundation and site facilities, an optional tracking system for larger antennas, and possibly an optional de-icing system. The IF and RF subsystem is generally located outdoors in a radio equipment shelter and consists of redundant high-power amplifiers with 25 to 500 watts of output power, depending on applications, up and down converters, IF combiners, and dividers. The redundant LNA is mounted directly to the receive feed in the antenna hub in order to reduce waveguide loss in the receive chain and enhance the receive signal quality. The baseband equipment configuration depends generally on vendors and network applications. However, this category of equipment can be organized into two groups. The common equipment, which includes power supplies, synthesizers, and uplink power control if required, and the channel equipment, which consists of the modems and codecs and various network interfaces. FCC and international regulatory issues since the early 80s have encouraged the development of VSAT networks in the United States. At international levels, the new frequency bands known as the KU and the KA are being gradually exploited, and smaller antennas can be used in conjunction with these higher frequency bands. Another significant regulatory event is that private or non-Intelsat carriers can now provide international communications via satellite, as long as they don't access public switched networks. In the United States, the telecommunications market is deregulated. The 1984 divestiture is a regulatory decision that has encouraged major telecommunications users to bypass AT&T and the Bell operating companies, or BOCs, in the delivery of telecommunication services. VSAT technology finds its strength in some of these bypass applications. In order to encourage the deployment of VSAT networks, the Federal Communications Commission provides special rulings that are very attractive to VSAT networks users. These are a one-time blanket licensing for all the VSATs to be installed, as opposed to the licensing of each individual VSAT node, and a long-term operational permit for up to 10 years without revision. An important factor in the emergence of easy-to-deploy VSAT networks is the current exploitation of the KU band and the future use of the KA band. These bands are dedicated to satellite communications and are not shared by terrestrial microwave systems. This significantly reduces the need for frequency coordination and terrestrial interference analyses. A major problem at higher frequency bands, however, is the signal strength reduction and distortion due to propagation and rain effects. Fades due to rain are local phenomena and depend on specific geographical locations. Tropical regions with heavy rainfalls generally incur deeper fades. Depending on the terminal location and availability requirements, fade margins of 4 to 12 dB are required to accommodate rain effects in KU band systems. Now, the applications of VSAT. On one hand, traditional methods of transmitting low and medium speed data, that is up to 256 kilobits per second, via multi-drop lines and microwave links, have recently fallen far behind the state-of-the-art technology, market trends, and the economic competition. Multi-drop lines are prone to rising and uncontrolled costs. They don't have the flexible topologies, which can easily be reconfigured, and they fail to support higher data speed requirements demanded by the computer-driven information age. VSAT technology, on the other hand, offers alternative delivery options, whereby data can now be moved point to multipoint quickly, accurately, reliably, and at low cost. Typical applications include financial services, where database users can receive, via satellite, real-time quotes, market trends, and other valuable information to help optimize investment yield. Potential users include banks, stockbrokers, private investors, and traders. Retail stores needing to provide large volumes of information to their branch offices can be very well served by VSAT networks. Services could include instant downloading of price changes, credit card verification, and inventory control data. The utilities companies can implement cost-effective supervisory control and data acquisition systems, or SCADA, using VSAT technology. Data downloading via satellite is also very compatible with the large volume requirements of electronic publishing, computer time sharing, data transfer, educational programs, and research information. VSAT networks can also be readily configured to support hotel and airline reservation services. In addition to data applications, VSAT systems can support star voice communications between the remote locations and the hub. Video can also be uplinked from the hub, feeding several VSAT locations with product introduction and promotion, training, and educational programs. The technical benefits of VSAT networks have significant economic advantages. Early VSAT users have reported fixed and predictable costs and up to 50% savings over multi-drop line solutions. In addition to the technical and economic advantages, VSAT technology offers strategic benefits to its users. It provides a full end-to-end bypass solution which allows total containment of the telecommunications costs as well as the control of the network reliability and performance standards. This concludes the presentation on the fundamentals of VSAT networks. Other tapes are available at George Washington University on satellite systems planning, design, integration, technology trends, and economics. Thank you for your attention.